So what we're going to look at now is we're going to be looking at DeMorgan's laws and some nested quantifiers. And where I want to start out with is I want to start out with some ideas of, or ways that we kind of represent quantifiers and compound quantifiers when what we're doing is we're learning how to work with this kind of logic. So what I've got here is I've got two statements. I've got n of x, x is green, and I've got m of x, x is fluffy. And so what you'll see here is you're going to see a table. And this table right here, it says, okay, here are the members of my domain. Numbers 1 through 6, they're the members of my domain. And for each one of these parts of the predicate, I have a truth value. So, for example, m of 1 is true. That means that 1 is green. Okay? And n of 1 is also true. Excuse me. M of 1 is true. That means 1 is fluffy. And then n of 1 is true means that 1 is also green. So, in fact, this individual is both. So what we see here, too, is that not only is m of 1 true, but m of 1 and n of 1 is also true. We also can think to ourselves that m of 1 or n of 1 is going to be true. Okay? Or we might also think that m of 1 implies n of 1. Because notice we've got true statement, that gives me a true statement. Okay? So that kind of helps me out in kind of thinking in terms of thinking about, well, what exactly am I seeing when I look at this particular table? Now what I can do here is I can actually work with some quantifiers. So for example, I might say for all x, m of x. And I want to know whether or not that's true or not. It's a bounded quantifier. I can figure that out. Well, that's actually going to be false because if you notice for 2, 3, and 6, we have that statement as false, so this here is false. But we could also ask, there exists an x such that n of x, and if you notice that actually is going to be true, notice that it's going to be true for 1. Okay? So that's going to end up being true. In addition, we might do something like this. For all x, we might say that m of x implies n of x. And what I need to do here is I need to make sure that I put the parentheses around the m of x and n of x, because otherwise this quantifier is going to just go with m of x and not with n of x. Okay? So what we always do with a quantifier is we actually pair them up with an individual predicate unless we put parentheses around and we want to say, okay, this is for all the x's within this particular statement. Okay? So if that's the case, what I want to look at is I want to see, well, is this true? Well, notice m of x is either true, true, true for 1, true, true for 4, and then otherwise we have falses. And so consequently, this statement here is true because that's the truth of conditional statements, right? If we have true, true, or we have false, true, or we have false, true, that we end up with a true statement. Okay? How about there exists an x such that m of x, or excuse me, n of x implies m of x. Well, if I look, I can see, okay, that actually is going to end up being true. That's true for like number 1, because we have true implies true. It's also true for number 4. That's also true. But the universal quantifier for the same state would end up being false, because in fact, for 2, 3, and for 6, we end up having true implies false, which ends up giving me a false statement. So what you want to see, there's a couple of things here inside of these examples. One is how we utilize a table that looks like this. 2, that relationship between the parentheses and where that quantifier goes. So when we see a quantifier in symbolic language, you want to make sure that if you are trying to quantify the entirety of a compound statement or a conditional, that you make sure that you are putting the entire compound statement in parentheses. And then 3, that we can utilize something like this in order to make statements about everything within a domain. So sometimes we actually define all the elements inside of a domain and their truth values for particular predicates in order to kind of like illustrate how it is that we work with these quantified statements. Now let's try this on our own. So here's the table. The table's at the left. And on the right-hand side, you can see these statements. And what we want to do, one, notice they're all bound, but two, also notice that we can determine their truth. So go ahead and pause the video for a moment and determine the truth of those 4 statements. All right, so now let's look at Q of 1 and P of 3. Well, if I look, Q of 1 is true, and P of 3 is true, so this ends up being true. Next, P of 2, if and only if Q of 3. Well, P of 2, if I look here, P of 2 is going to end up being true. Q of 3 is going to end up being true. And if you remember, this biconditional is only true if we have both true and both false. We have both true in this case, so we get true. All right, now number 3. For all x, P of x or Q of x. So what this means is that either for every x value that we have, 1 through 5, the members of my domain, either P of x is true or Q of x is true. So I go in here and I say, okay, well, what about P of x? Is P of x true? Well, I've got, do I have anywhere it's both false? Well, notice that for 5 is false, false. And since 5 is false, false, P of 5 is false, Q of 5 is false, what we have here is we have a statement where we get false for the or. So P of 5 or Q of 5 gives me false, and that means the universal is also false. And then there exists an x, P of x, if and only if Q of x. So is there a statement where we actually have a true biconditional for a single x, by the way? So unlike number 2 where we had 2 and 3, we actually had different values. In this case, the x has to be the same in both cases. So I go in here and I look and I see, oh, that could be true for 5 because false, false gives me true. Or it also could be true for 3 because true, true, or for 2. So in this case, there is one of them, and that means that that statement is true. And that's actually how we do this. All right, so let's look at another example. We're now going to look at this one, which is Q of xy. And so Q of xy, we actually now have 2 variables. We have x, we have y. So what we're going to do here is I'm going to define my x values to be the ones on top and my y values to be the ones on the side. And that's just for my purposes. And what I want to do is I want to determine, like say for example, we want to say, okay, what about Q of 1, 7? Okay, Q of 1, 7. So Q of 1, 7, what I'm going to, or excuse me, 1, 6, not 1, 7. Q of 1, 6, if I go down here and I've got my x value is 1, my y value is 6, I see that that statement is true. Okay? Or what about Q of 2, 4? In this case, 2 is my x, 4 is my y, and so that equals false. What about Q of, now say for example, we give Q of 4, 3, and Q of 5, 1. Notice, we're going to have my x value be 5, my y value is 1, so that's true. And so here I get true. And then Q of 4, 3, I've got 4, and then 3, that's true. So true and true, so this means that this ends up equaling true. So this is a different kind of truth table that we might get for these kind of predicates. All right, and we're going to see that this kind of truth table is going to be really handy when we get to things called nested quantifiers. And so we want to make sure that we know how to read one of those as well. Okay, so now I have DeMorgan's laws for quantified statements. So we've got a whole set of, if you remember the DeMorgan's laws, what happened is that if I negated, I ended up negating, bringing the negation inside and then changing the sign. Well, we're kind of going to do the same thing basically for the DeMorgan's laws for quantified statements. Let's say, for example, that what I have is I have a predicate. I have predicate Q of x, and I have utilized the universal quantifier for all x, and then I choose to negate it, right? So I'm going to go in and I'm going to negate for all x Q of x. Now, what I want to think about is I want to imagine, so we're going to let the domain of x, right, of our values, we'll call them, let's say, for example, x1, x2, x3, and we're just going to go down to xn. So we're going to have n values within this domain. So if I write this, what this means to have for all x q of x, that actually means that it is true that q of x1, q of x2, q of x3, all the way to q of xn, right, are all in fact true. All right? So they're an and statement. That actually ends up being an and statement. So I get q of x1 and q of x2 and q of x3, okay, all the way up through q of xn. And that is what we get when we actually take a quantified statement, all right, and we expand it out. We're saying, in fact, for all q of x, all right, for all x, q of x means that it is true for every element, and so hence that's an and statement. Now, if I go through and I negate it, I'm going to negate here, okay, so I negate that the statement, so I'll negate on both sides, like algebra. What I know now from my DeMorgan's laws is that this left-hand side becomes for all q of x1, or excuse me, negates q of x1, and then I switch the sign. And I negate. Okay, so this now becomes all ors. And we have the negation within each one of the ors. Now, what I want you to notice here is that this is actually my existence statement. So this statement here, where I have all these ors together, they're only going to be true if one of these values is true. So at least one of, and we'll call this the negation of q of xi, doesn't really matter, any q of x, like, is true. That will end up giving me a true statement. Otherwise, I've got false. Like, if they're all false, it's all false. And so what is that, right? At least one, that's existence. Okay? So this equals then, there exists an x such that not q of x. So now, what we've done is we've had each one of the values within, or that are within, that are next to our or statements, is a not q of xi, okay? So that or statement becomes the existence statement, and we end up with there exists a not q of x. If we kind of think about this, if you sit down and you think about it, it does make some sense. The statement for all x q of x means that every single value, for every single value in the domain, x1 through xn, q of x is true. Well, how do we know that it's not true? If there is at least one that has it be not true. Okay, that has q of x not be true. And so consequently, that actually is the statement, there exists an x such that not q of x. So these two end up being logically equivalent. And we write that out as a logical equivalence. We say, okay, not for all x, q of x is equivalent to there exists an x such that q of x. Okay? And that's my DeMorgan's law. Call it DeMorgan's law number 1. Basically, just like the DeMorgan's laws that we saw before, what we're going to do is we are going to go in and we're going to bring the negation in, and then we're going to flip the sign. And in this case, the sign is the quantifier. Okay? So bring the negation in and flip the quantifier. If we take a look at the other way around, let's say, for example, I have not, there exists an x such that q of x. If I think about this, what this is that this is not q of x1 or q of x2 or going all the way up to q of xn. Symbolically, because I'm using my DeMorgan's laws, this changes to not q of x1 and not q of x2 and all the way up to not q of xn using DeMorgan's. And then if I look, what is that? That's going to equal then, or it's going to be equivalent to, excuse me, it's going to be equivalent to for all x, not q of x. Because notice, I'm saying every single value of x, Q of x is going to end up being false. All right? Because, well, that's exactly what this says. That's the only way to get true. If Q of xn is false for every single x. Okay? And so, consequently, this is our other, call it DeMorgan's Law 2, and that is not there exists an x, Q of x is equivalent to for all x, not Q of x. And if you think about that one, logically it makes sense too. Basically it's saying if it is the case that we don't have a Q of x be true, that means that every single Q of x is false. Right? And that's our logically equivalent statement, and those are the DeMorgan's laws. Now what we want to look at is we want to look at these nested quantifiers. So a nested quantifier is going to be something that we use. It's going to be multiple quantifiers that we use whenever we have a statement that has multiple variables. Okay? And oftentimes we're going to need this because otherwise what we'll end up with is we'll end up with one of those free predicates, and that ends up being not a proposition. So there are four, if we are looking at two variables, we're going to have four different kinds of nested predicates. If we have three variables, we'll have six. And that's because we've got the number of variables, like x, y, and z, that's three variables, times the two choices, the universal and the existential. So 3 times 2, 2 times 2, that's going to give us how many different options that we have. Let's take a look at this example here of p of xy, and I've drawn a table for p of xy like we did earlier. Let's say, for example, we start out with for all x, there exists a y such that p of xy. What this is saying is that for every x, I can find a y that makes p of xy true. So let's say, for example, I look at this table, and I'm going to have that my y's are going to be here on this horizontal, and my x's are going to be on the, y is going to be on the vertical, and x's are going to be on the horizontal. So what I'm going to do now is I'm going to say, okay, well, if my x is 1, okay, so there's x is 1, do I have a y that gives me a true statement? So p of 1, 1 is true. Awesome. Now let's say, for example, x is 2. So x is 2. Do I have a y, okay, that makes p of 2 true? So this is p of 2, 1 is also true. Great. Okay. What about p of, let's p of 3. So p of 3, when I look at p of 3, well, p of 3, I could choose 1, I could choose 2, I could choose 4. They're all going to be true. Let's just say that p of 3, 1 is true. Okay? How about p of 4, 1? Well, p of 4, 1 is also true. So what you see here is that for every x that I have, there is at least one y that gives me it to be true. Okay? In most cases, there's more than one y. But, you know, we didn't need that. We only needed that there at least one y. For every x, there is at least one y that makes p of xy true. And that's that statement. Let's switch it around. What if I wrote it like this? There exists an x for all y such that p of xy. Our normal thinking is, isn't that the same thing? Well, no, it's not. Okay? In this case, I want to see, can I pick an x, any one x, such that for every y, I get a true statement. Okay, so it's almost like this. All right? So I'll pick my x first, and then I want to see if once I pick x first, can I figure out a y that makes every one of these statements true? Or excuse me, once I pick my x, is there any y that has all trues? So for example, if I look at 1, so like I look at 1, I've got p of 1. P of 1 doesn't work because p of 1, 2 is false. So not p of 1. What about p of 2? Well, I already know that p of 2 is not going to be true because I know that although p of 2, 1 is true, all the other values are false. Okay? So p of 2 is also false because we don't have all of our y's to be true. What about 3? Well, 3 is a problem because p of 3, 3 is false, right? So when I choose x to be 3, right, I'm going to hold x to be of the value, and then I'm going to see whether or not all the y's are true. we end up with a false statement, so P of 3 is false. And then if I look at 4, you can see that 3 and 4 are also false. So P of 4, false. Okay? So consequently, this statement here is going to end up being false. What if I change the variables, though? What if I have there exists a y for all x, such that P of xy? Now I have this. Well, let's take a look. If I select y equals 1, here's y equals 1, right here. That's that first line, y equals 1. Notice that when y equals 1, every single truth value ends up being true. That means for all x, right? For all x, P of 1y, or excuse me, P of x1 is true. So what we get here is I set y equal to 1, and then I look at for all x, basically P of x1. That's true, so consequently, this statement here is true as well. It's kind of a tricky idea. You kind of have to think your way through it. It can be a little bit challenging. Okay? The other ones, the there exists, are a lot easier to think about. I got there exists and there exists an x. There exists an x and there exists a y such that P of xy. In this case, we can choose any values as long as there is a single truth value in the entire table, right? We have this truth. So basically what this is saying is I pick an x, there exists an x, such that I could pick a y that gives me truth here. Okay? And so consequently, this is ended up being true. So like, for example, P of 1, 1 is true. And so that existence statement, the double existence, actually ends up being true. If I have both universal for all x and for all y, P of xy, you can actually see that this is going to end up being false. So for every x, we get for all y, P of xy. Well, that's not true, right? What we're going to end up seeing is that we've got a single example. All we need is one example, although sometimes more. And in our single example, we end up with, say, for example, P of 1, 2 is false. So that actually makes this statement false. Because when we have both of the values being universal quantifiers, it actually requires every single value in the truth table to be true. And that's just not the case. Okay? So let's kind of review a little bit. If I put the universal quantifier first, if I put the universal quantifier first, what I'm saying is I'm going to check for every x, there's a single y, okay? Right? Such that I get P of xy. All right? And you'll notice that ends up being true. For every x, there's at least one y that P of xy is true. Notice it works for 1. We also can see that, like, if I had chosen 3 for 1, 2 for, 3 for 1, 2 for, 1 for 2, 1 for 3, and maybe 2 for 4, that's also going to give me a true statement for existence if we just hold our x's. If we select any x that we want, we'll find at least one y. The harder one to think about is this one here. When we put the existential one first, there exists an x for all y such that P of xy. And what that's going to do is it's going to say, okay, well, I am going to hold my x's, right? I'm going to say, all right, well, select an x. Let's say I choose 1, okay? And so for all y, I want to see, am I going to get a true statement? Well, it's not true. It's not true for 1. It's not true for 2. It's not true for 3. And it's not true for 4. Because in each one of these values for x, okay, we have at least one y being false. But if I switch it around, and I say there exists a y for all x P of xy, if I pick y equal to 1 now, you can see that I can change my x's, okay, and it gives me a true statement for every single one of those values, right? Basically, P of x1 is true for all values of x, and so consequently, this nested quantified statement is also true. Kind of a tricky idea. It's kind of hard to get through. Let's take a look at another example, and we'll work on another example. Okay, so let's take a look at this truth table. We'll take a moment to draw it in, and then we'll give you some questions that we should work with. So we'll first start with 1. There exists an x for all y such that p of xy. Now, I want you to notice that I made the y's now my column numbers and my x's my row numbers. We'll take 2. Let's do for all x, for all y, we'll have p of xy. Then we'll have there exists a y for all x such that p of xy. And then we'll have for all x there exists a y such that p of xy. Okay? So let's take a look at this. Pause this video for a moment and see if you can figure this out. So let's take a look at this first one. There exists an x for all y such that p of xy. So what we're going to do is we're going to say, okay, let's first select a value for x. So we'll first let x equal 1. Right? We'll do a little scratch work down here. We'll let x equal 1. So if x equals 1, I want to see if all of my y values, all of the y's, are in fact true. Well, notice that when y is 2, we get false, so it doesn't work for x equals 1. Then I go down and I check x equals 2. So I check x equals 2, and I look and I see, oh, notice that if y equals 2, I end up getting false. Okay? So this is false. This one's also going to be false because, again, I got a false statement. Then I'm going to go down to x equals 3. I'll try the third one. And what I get is that when y equals 3, I get a false statement. So once again, I got false. So I've got all 3 are false. All right? So we end up with false. There does not exist an x such that every y ends up giving me true. All right, let's take a look at the second one. For all x and for all y, p of xy. Well, that's going to be false. That's false because we have at least one false statement in the table that ends up being, well, any value that actually has a false, so this is false. What about number 3? There exists a y for all x. Well, now I'm going to set my y's. We're going to do a little scratch work down here. I'll set my y's and check all my x's. All right. So I'll take y equals 1. When y equals 1, oh, look at that. It's true, true, true. Okay. I get all trues. And so consequently, this ends up being true. Okay. If y equals 1, p of, we'll call it x1, is true every single time. So consequently, that nested quantifier ends up being the true statement. Now, what about the fourth one? For all x, there exists a y such that p of xy. Well, let's check. Okay, so I'm going to start out with my x equals 1. Again, so here's my new little scratch work. When x equals 1, oh, all I need is one true statement. So I got p of 1, 1 is true. Great. So that works. How about x equals 2? When x equals 2, I got p of 2, 1 is also true. That works out well. Awesome. And then what about when x equals 3? Okay. Well, when x equals 3, I get p of 3, 1, and that's also true. And so consequently, what I get here is that this is a true statement. It actually makes sense that because there exists a y for all x is true, means that for all x there exists a y is true. They're kind of equivalent statements in many ways. All right, when we kind of think through them. Let's say we want to do 5 and see a little bit different. For all y, there exists an x such that p of xy. Let's do this one. Now, we'll take a look at y equals 1. When y equals 1, okay, we know that we have true statements there, so that's actually going to end up being true. Okay, y equals 1. X equals 1 gives me true, x equals 2 equals true, and x equals 3 equals true. When y equals 2, we know that x equals 3 gives me true, so that actually gives me a true statement as well. Okay, and then when I go with the 3, okay, I look down here, I've got when x is equal to 1, so when y equals 3 and x equals 1, I get true as well, so this one is also going to end up being true. Okay, so hopefully that clarifies how it is that we determine truth whenever we have nested quantifiers. All right, it's kind of a tricky idea, But in some ways, you can kind of like work through things mentally in order to determine truth for these nested quantifiers. Given the fact that now we've talked about nested quantifiers, we should talk about DeMorgan's laws for these nested quantifiers. And it makes sense that it kind of just progresses from our other DeMorgan's laws. So for example, if I have for all, the negation of for all x and for all y, p of xy, that's going to end up being equivalent to, what we'll do first is we will switch the sign for all there exists an x, such that not for all x p of xy. We'll start there, and then we'll move the quantifier in again, and so this is going to end up being there exists an x, and there exists a y, and then not p of xy. So basically what we're going to do is every time we move in the negation, we're going to switch the signs. So like say for example, if not for all x there exists a y, such that q of xy, that's going to end up being there exists an x, such that not for all, not there exists an x, there exists a y, q of xy, and that will then be there exists an x for all y, not q of xy. So from a symbolic logic standpoint, it's probably easiest to just think about it from a symbolic logic standpoint, because it gets kind of complicated to try and think through all of the logic that goes into this. But it turns out that it is exactly that. It's exactly right. Okay? So essentially when we're working with DeMorgan's laws for nested quantifiers, what we want to do is we want to, every time we move in the negation, we move it in one at a time along each one of the quantifiers, and then we will switch the quantifier. Okay? And that's how we do DeMorgan's laws. So this was a longer lecture. It had to do with, some of our quantified statements, understanding how it is that we determine truth utilizing quantified statements, our DeMorgan's laws for quantifiers, nested quantifiers, and then our DeMorgan's laws for those nested quantifiers. And so what that should do is that should give us an idea of how it is that we utilize quantifiers in order to do logic, in order to prove logical